this computer. We just started recording. Hello, everybody, and welcome to the Graduate Online Combinatorics Colloquium. Today we have Hoi Yip, who's going to tell us about improving the trivial upper bound on the clique number of Paley graphs and generalized Paley graphs. Before he starts talking, I want to just remind everybody of the sort of guiding principles of the Graduate Online Combinatorics Colloquium, which is that there's three of them. First of all, we are all learning. Second, everyone has something to contribute. And three, no one has all the answers. These are sort of expanded on in our community statement on our website. But briefly, this means like ask questions. If the speaker doesn't have the answer, maybe we'll come up with the answer together. And Andres and I will be monitoring the chat. So if you can't unmute and ask your question directly, feel free to ask it in the chat and either Hoi will see it or Andres or I will sort of unmute and ask ourselves. Okay, without further ado, Hoi, take it away.
Thank you for the introduction. It's a great pleasure for me to speak at GOCC. In this talk, I will mainly talk about how to improve the trivial upper bound on the clique number of Paley graphs or generalized Paley graphs. So let's first define what is a Paley graph. So we need a prime power Q, which is congruent to 1 modulo 4. And the Paley graph PQ is defined on the finite field FQ. So the vertices of this graph is FQ, and the two vertices are adjacent if the difference is a quadratic residue in FQ. And we need this condition Q congruent to 1 modulo 4 because we want this graph to be an undirected graph. And this is a figure of a Paley graph with order 13. We can see that, for example, 1 and 2 are adjacent because their difference is 1, which is obviously a square. But 1 is not adjacent to 3 because you can check that their difference 2 is not a quadratic residue, modulus 13. And this is a beautiful picture about Paley graph with order 41. So you can see that Paley graphs are very nice because they have some kind of symmetry. Similar to the Paley graphs, we can also define generalized Paley graphs. To do that, we need to fix a positive integer d, which is larger than 1. Then we can define the d Paley graph on FQ. It's denoted as PQD, and the vertices of this graph is again FQ, the finite field with Q elements. And the two vertices are adjacent if their difference is this power of some x in FQ star. So notice that the two Paley graphs are just the standard Paley graphs. And for three Paley graphs, we also call that cubic Paley graphs. Let's consider some some restriction on the parameters d and q. So because FQ star is a cyclic group, then if we consider two different d, namely d and d prime, if the GCD d and the q minus 1 equals to the GCD of d prime and q minus 1, then it's easy to check that PQD and PQD prime are isomorphic. So we can always assume that d is divisible by q minus 1. That would be very convenient. And also, because we want this generalized Paley graph PQD to be an undirected graph, we need -1 to be this power in FQ star, which means q minus 1 over d is an even number. So with these two conditions in the following discussion, we will always assume that q is congruent to 1 modulo 2d. That will be convenient for our future arguments. And the importance of Paley graphs and generalized Paley graphs is that they connect many branches of mathematics, such as combinatorics, in particular, some kind of algebraic graph theory, and it also connects the clique number of Paley graphs and the Ramsey diagonal Ramsey numbers. It's also related to number theory, in particular Cartesian sums. And because Paley graph and the generalized Paley graphs are nice graphs, they have many nice graph theoretical properties. So they are important in design theory and coding theory. In this talk, we will focus on estimating the clique number of Paley graphs and generalized Paley graphs. So let's recall what's the meaning of the Paley graph of an undirected graph. So if G is an undirected graph, the clique number of G will be denoted by omega G. And omega G is just the size of the maximum clique of G. And the clique is just a complete subgraph of the graph G. Finding a reasonably good upper bound for the clique number of a Paley graph is an old and open purpose in additive combinatorics. So that's why we are interested in finding and improve upper bounds on Paley graphs. This is a table of clique numbers for Paley graphs of order less than 340. So this numerical evidence suggests that omega pq behaves like a polylog function in Q, unless Q is a square. So for example, if Q is 169, the omega will be 13, while if Q is 289, the omega pq will be 17. So we can see that we may conjecture that omega pq is root q if q is a square. And we will see that this is not a coincidence. We will see that in the next few slides. So unless q is a square, omega pq behaves like a polylog function in Q. And for the lower bounds in 1988, Cohen showed that the clique number of this generalized Paley graph PQD is at least half times log DQ plus a constant of 1. And in 1990, Graham and Reynolds showed that omega PP is capital omega log P log P. So that means we can find an infinite sequence of primes P congruent to 1 modulo 4, such that there exists a constant C, where for each primes in this sequence, we have the clique number of PP is at least C times log P log P. Furthermore, if we assume that the generalized Riemann hypothesis is true, then Montgomery showed that this omega bound can be improved to omega log P log P. Okay, so this is the lower bound. So the lower bound is just some kind of polylog function, and this is the best known lower bounds. However, in some cases, the lower bound can be significantly improved. So we have this kind of theorem on the lower bound. So suppose Q is congruent to 1 modulo 2D, and I is the largest integer such that D divides Q minus 1 over P to the R minus 1. Then the clique number of PQD will be at least P to the R. And the idea of the proof is that we can show that Fp to the R is a subfield of Fq. And we can also show that this subfield indeed forms a clique in PQD. So with this basic construction of the clique, we can show that the clique number is at least P to the R. And perhaps it's difficult to estimate what's the size of R. So we can have this kind of concrete corollary. So if Q is P to the S and D is a prime such that 2D divides Q minus 1 and also D divides S, then we can show that the clique number is at least Q to the 1 over D. So again, the proof is that we can consider this subfield FQ to the 1 over D, and we show that this is indeed the subfield of FQ, and we show that this forms a clique. So this is the lower bound. And for the upper bound, we have this kind of obvious upper bound, which is Q minus 1 over D plus 1. And the proof is actually very simple. So we consider maximum clique C consisting of elements V1, V2 up to Vn. Then by the definition of the generalized Paley graphs, we have V2 minus V, V2 minus V1, V3 minus V1, up to Vn minus V1. They are all distinct and they are all these powers in FQ star. So because the number of these powers in FQ star is exactly Q minus already, then it follows that the upper bound of the clique number will be Q minus over D plus 1. Okay, so this is the obvious upper bound. And in my title, I said trivial upper bound. So the trivial upper bound is given by root Q, and it's appeared a few times in the literature. And there are many proofs towards this trivial upper bound. And I just pick the simplest one for our presentation. So again, we consider a maximum clique C consisting of the elements V1, V2 up to Vn. And we also take G to be a primitive root of FQ star. And we consider this set W, which is Vi plus GVJ, where I and J are between 1 and capital N. And our goal is to show that every these kind of elements are pairwisely distinct. So if that's the case, then the size of W will be N squared, and N squared is less than Q. So N is most through Q. And to see that, suppose two elements in this set are the same. So assume Vi plus GVJ equals to Vi prime plus GVJ prime. Then we can do some manipulation to get Vi minus Vi prime equals to G times Vj prime minus Vj. And by the definition, Vi minus Vi prime and Vj prime minus Vj are both these powers in FQ, but G is not this power because G is a primitive root. So so it follows that this equation can hold only if both sides are equal to 0. And that means I must be equal to I prime and J equals to J prime. So we have shown that these kind of elements are pairwisely distinct. So we have this kind of trivial upper bound, which is root Q. Okay, and next I would like to show that trivial upper bound is sometimes tight. So recall that we have this kind of theorem on the lower bound, and the root Q is the trivial upper bound. And it turned out that in this special case where Q is a square and D divides root Q plus 1, this lower bound theorem says that the clique number is at least root Q. But this upper bound theorem says that the clique number is at most root Q. So that means in this case, the clique number must be exactly root Q. And in particular, if Q is a square and if we take D to be 2, then because Q is an odd number, we always have 2 divides root Q plus 1. So that means for a Paley graph of a square order, the clique number will always be root Q. So that explains why in that table, for Paley graphs with square order, the clique number is root Q, but for others, they behave like a polylog function. Okay, and it turned out that improving this trivial upper bound root Q is extremely difficult. And until last year, the best upper bound was root Q minus 1 for non-square Q. So it just improved the trivial upper bound by 1. And that's the result by Becker, Ruza, and Mataresi in 2013. And earlier this year, there was a breakthrough towards this problem. So Hansen and Pagedes proved that for this kind of generalized Paley graph PPD, the upper bound can be improved to about root P over D plus a constant. So recall that the trivial upper bound is root P, but they are able to show that the upper bound can be bounded by root p over d as a constant, small constant. And they use some kind of polynomial method. And later this year, Di Benedetto, Soimosi, and White recover the same bound using a different idea, which we will talk about later. So Soimosi is my my advisor, and these are two PhD students of him, which are also my friends. One natural question to ask is that whether this bound also holds when we replace P by a prime power Q. And the answer is unfortunately no, because the method only applies for the prime field Fp, but not for Fq. And we will see why in the next few slides. Okay, so the main motivation of the research project I did in the past few months is to generalize this bound to PQD, where Q is the prime power, because this bound only was for primes P, but not for prime power Q. Okay, so our first result is that if Q is a non-square, then we can bound the clique number of PQ to be about root Q over 2 plus some small terms. So here Q is P to the 2s plus 1, so this dominant term will be about P to the s plus half. And these kind of terms are lower terms because they are of the order P to the s. So we can see that this is consistent with this bound. Because when P is a prime and when D is 2, this is about root P over 2. So this is about root Q over 2 plus some small terms. But I have no idea to improve this kind of lower terms to be a constant term. Because in FQ, there are many things to worry about. Mainly because that FQ has characteristic P. So some bad thing can happen. Okay, and let's try to briefly describe what Hansen and Pachidis did. So they use a particular polynomial method called Stepanov's method. And the idea is that we consider a maximum clique C. And our aim is to construct a non-zero polynomial f with low degree, such that each root ai vanish with a high multiplicity. And suppose this is the case, then we can try to get an upper bound on the size of the clique, which is capital N. So suppose the degree of f is d, and suppose each root ai is the root of multiplicity at least k. Then we can just use the degree bound because f is a polynomial with degree d. It has at most d roots, but we have shown that it has at least capital N times k roots. So we have capital Nk is at most d, and it follows that N is bounded by d over k. Okay, so because we want to give an improved upper bound on capital N, then we want to minimize the right-hand side, which is d over k. So that's why we want this polynomial f to have 0 degree. And we want this k to be large, which means each ai vanish with a high multiplicity. And we need to be careful because this polynomial must be a non-zero polynomial. Otherwise, this statement is not true. So the issue with Hansen and Pachidis proof is that if we just apply the polynomial they use to FQ directly, then there are some cases where the polynomial is identically zero polynomial, so we cannot use the polynomial directly.
So,
and
sorry, a small question. What was Stepanov's method developed to find? Like what was, so I see you've got a maximum clique and you've constructed a polynomial. What's the output of the method?
The output of the method is the upper bound on capital N.
Okay.
So we have f,
Click.
the degree of f is d, and the
Mhm.
multiplicity is at least k. Then the output is that the capital N is at most d over k.
So this gives you this method would give you an upper bound on the maximum clique size.
Yeah.
Okay. Is it obvious why like studying a polynomial is the right thing to study to find?
So I guess recently there are many results using polynomial method in the application. I mean to apply a polynomial method in combinatorics, and I guess Larry Goose even has a book called a polynomial method in combinatorics. So that's a hot topic, and I'm not sure why they introduce such kind of polynomials, but perhaps this kind of polynomial capture the the properties of the probes.
Okay.
Okay. Yeah.
Okay.
So we will see that the polynomial they constructed actually capture the properties of the problem.
Okay.
Okay, so now we would like to check whether whether AI vanish with a high multiplicity. And the idea is to use the derivative, and we have this kind of well-known lemma. So suppose f is a field with characteristic 0, and suppose C is the root of f n x for n equals to 0, 1 up to m minus 1. Then C is the root of multiplicity at least m. So this is nice. So we can check the derivatives to see whether C has a high multiplicity. And however, this result fails to hold for fields with non-zero characteristic, because if we consider a field with positive characteristic, and we know that the characteristic must be a prime number, then for any polynomial f in this ring kx, if we take the piece order derivative, it will be identically 0 because the derivative consists of a factor of p, which is 0 in this characteristic p field. So that's the issue. But this can be overcome by introduce a different type of derivatives called hyperderivatives. And I believe this is also called Haas derivatives. So the idea is that we need to introduce the binomial coefficient into the derivatives. So with the help of that, we can overcome the non-zero characteristic. Okay, so the derivative is very similar to the definition of the hyperderivative is very similar to the usual derivative, but we need to introduce this kind of binomial coefficients. And we also have a similar, we also have an analog of this lemma. That is, if C is the root of this kind of hyperderivatives for n equals to 0, 1 up to m minus 1, then C is the root of multiplicity at least m. So note that in this lemma, we don't need to worry about the characteristic of k, because this kind of binomial coefficients help us to avoid the characteristic issue.
So I have a follow-up question then, which is, why is it called a hyperderivative, and is it related to hyperfields?
I don't know why it is called hyperderivative. So probably some authors use this kind of definitions first, and then people follow their notation. And I guess this is also called Haas derivative because Haas first defined them. Okay. Okay, so with the hyperderivatives and step-source method, we can try to find a upper bound on the key number. And to do that, we need an intermediate step. So suppose Q is congruent to 1 modulo 2D, and suppose capital N is the size of the maximum clique. We need to introduce an additional parameter little n, where little n is bounded by capital N, and the little n satisfies that this binomial coefficient does not vanish. The purpose of this condition is that we want the polynomial we constructed to be a non-zero polynomial. So I guess that's crucial. And if this condition is satisfied, then we have capital N minus 1 times little n is bounded by Q minus 1 over D. Okay, so let's try to see the idea of the proof. And again, we take C to be a maximum clique, and the elements in this C is A1, A2 up to AN. Okay, and this is the polynomial we are interested in. So this is a modification of the polynomial Hansen and Pachadis use. So I just modified them a little bit so that it works in FQ instead of just working in FP. Okay, so
one quick question about the notation. Is the -1 inside the sum or outside the sum?
Outside,
Okay.
sorry. Yeah, so the polynomial will be the summation of Ci times x minus Ai to the n minus 1 plus Q minus 1 over D. And then finally we subtract 1. And this kind of coefficient Ci comes from the this system of equations. Okay, so we may notice that the coefficient matrix of this system is a Vanderbilt matrix. And this Vanderbilt matrix has parameters A1, A2 up to AN. And because they are all distinct, this coefficient matrix is invertible. So we can guarantee that this system has a unique solution C1 up to Cn. Okay, so this system basically says that for each j from 0 up to n minus 2, the sum of Ci times minus Ai to the j is 0. However, when j is n minus 1, we want this sum to be 1. Okay, and next we would like to determine the degree of f, and we also would like to see whether each root vanish with a high multiplicity, because that's the idea of using Stepanov method. Okay, so first let's check the degree of f. So for each coefficient, we can use the binomial expansion to see the coefficient of a particular term. So for example, for this, the coefficient of x to the n minus 1 plus q minus 1 over d minus k, then just using binomial expansion, the coefficient will be this binomial coefficient times the summation of this Ci times minus Ai to the k. And the magic is that by our construction, this is 0 when k is from 0, 1 up to n minus 2. And when k is n minus 1, this is 1. And we assume that this is non-zero in our assumption. So that means the coefficient of x to the q minus 1 over d is non-zero. So we have verified that the degree of f is exactly q minus 1 over d. Okay, so that's nice because if you directly check this polynomial, you may see that the degree is bounded by little n minus 1 plus q minus 1 over d. But we are able to show that this is actually q minus 1 over d. And next, we would like to see each root has a high multiplicity. And firstly, we would like to show that each aj is indeed a root of this polynomial f. Okay, so we just write down the definition of faj. which is the summation of this, and then finally -1. And now we will see this polynomial capture the properties of the probing, because by definition of the generalized Paley graphs, each aj minus ai is this power in FQ star. So if we take the q minus 1 over d power, then it becomes 1. So that means we can remove this power to get this n minus 1 power. And after getting this, we can use the binomial theorem to expand this sum. And again, we can collect the sum in this way, so that we can use our construction of CI. So this sum is usually 0 unless L equals to n minus 1. So finally, we can show that Faj is 0. And similarly, we can show that the high order hyperderivatives also vanish at aj for k from 1 up to n minus 2. And if j is between n plus 1 and capital N, then we additionally have e to the n minus 1, Faj is 0. Sorry. So to conclude, we have shown that each of the root a1 up to a little n, they are roots of f of multiplicity at least n minus 1. And for other roots, they are of multiplicity at least little n. Then we can use the degree bound to conclude that capital N minus little n is bounded by the degree of f, which is q minus 1 over d. Okay, so let's conclude the proof of this intermediate step. Okay, and next, let's see how can we apply this intermediate step to prove our main theorem. Okay, so because we have additional parameters little n here, so if we try to get the best upper bound on capital N, then we need to find the largest little n bounded by capital N, such that this binomial coefficient is not congruent to 0 modulo P. And after finding that largest little n, then we can solve it by, for example, using quadratic equations to solve it. But we need to see how binomial coefficient behave modulo P. And very useful tool in determining that is the following Lucas theorem. So if P is a prime and M and N are integers, then we can write them in base P representation like this. Then Lucas theorem basically says that M choose N is basically the product of Mj choose Nj. So we just need to write them in base P representations and find the binomial coefficient in each digit, and we multiply them. And the nice thing about this Lucas theorem is that for each digit, Mj and Nj are always bounded by P minus 1. So it's very easy to check whether this binomial coefficient is divisible by P. Okay. Okay, so recall that we need to find the largest little n bounded by capital N, such that this binomial coefficient does not vanish. And we demonstrate the idea of the proof for the case q equals to p to the 2s plus 1, where s is at least 2. Okay, so we need to write capital N minus 1 as this kind of base P representation. And there will be two cases. The first case is that this digit is relatively small. Then we can pick n minus 1 to be this one. So we can keep the first two digits. And for the remaining digit, we want them to be as large as possible, but we want them to be bounded by p-1/2. So if we pick this little n in this way, then we can see that the difference between capital N and little n will be relatively small. And we can use Lucas theorem to show that this is non-zero. Because, for example, for this term, because we have assumed that J prime is bounded by p-1/2. So this one is always bounded by p-1. So we know that this won't be 0. Okay, and similar for these two terms. And the second case is that this digit Js-1 is relatively large. And in that case, we need to pick a different little n. So we just keep the first digit, and for the remaining digit, we just pick them to be p-1/2. And again, the difference between capital N and little n will be relatively small because we keep the largest digits. And we can check that this is non-zero by Lucas theorem. It should be simple. Okay. Okay. So with that, we have shown that we can always find a little n that is close to capital N. So the difference between capital N and little n is relatively small. So so roughly speaking, we have n squared is at most q/2. So if we solve that carefully, then we can get this kind of upper bound. And the dominant term will be root q/2. And these are some lower terms. Okay. Okay, and the next question is that because this is the bound for Paley graphs. So how about generalized Paley graphs? And we know that the simplest generalized Paley graphs should be cubic Paley graphs. So that's PQ3. And our second main result is that we show that the trivial upper bound UQ can be improved to something like 0.769 UQ plus 1, unless the clique number is 2Q for obvious reasons. I mean, if F2Q is a clique, then the clique number must be root Q. So unless F2Q is a clique, we can always improve the trivial upper bound by a multiplicative factor. Okay, and let's try to sketch the proof of this. The proof will be very similar but more complicated. So again, we would like to find the largest little n bounded by capital N, such that this binomial coefficient does not vanish. So the first thing we need to do is to understand the base P representation of Q-1/3. And in this case, there are actually two different cases, two different patterns on Q-1/3. The first case is P is congruent to 1 modulo 3. In this case, the this base P representation will be very simple because every digit is exactly P-1/3. And the second case is that P is congruent to 2 modulo 3. In that case, the base P representation will have a period 2, and in each period it will be P-2/3 followed by 2P-1/3. So to prove this theorem, we just need to separate the problem into two different cases, and we do and for each case we try to find this kind of little n. Okay, and the next question is that whether this kind of idea can be generalized to generalized Paley graphs with D greater than 3. And again, we need to understand the base representation of Q minus 1 over D. So we know that the base representation will always be periodic, and the period delta will be actually the order of P modulo D. And by Euler's theorem, delta will be a divisor of phi D, where phi is the Euler phi function. So we can see that if the number of divisors of phi D is very large, then Q minus over D will have many different patterns. So so the argument will be very complicated, because for each different pattern of Q minus over D, we need to provide a particular way to find a little n optimally. Okay. And okay. Okay, I guess I still have about 15 minutes. Okay.
Yep.
Yeah. Okay, so let's go to the second approach towards this problem. We will see the connection between the number of directions formed by a Cartesian product and the clique number of generalized Paley graphs in the next few slides. But let's first introduce the definition of this number of directions. So let AG2Q denote the affine Galois plane over the finite field FQ. And if U is a subset of AG2Q, we can just use Cartesian coordinates in AG2Q. So we can set U to be xi, comma yi, where I is from 1 to up to the size of U. Then the set of the direction determined by this point set is just the set of the slope of the line formed by 2 points. So suppose this is xi yi and this is xj yj. Then they form segments, and the slope of this segment is called the direction. So we can see that the direction is a subset of FQ, but it's also possible that the denominator will be 0. In that case, we call this direction infinity. Okay, so the possible values of the size of D has been studied by many authors, and this result is a famous result by Sony in 1999. So basically he showed that if we consider a point set in this affine Galois plane AG2P with size at most P, then either U is contained in a line or U determines at least about U over 2 directions. Okay, so that means for any arrangement of the points in this affine plane, the number of direction will be huge in this case. But when the underlying field becomes FQ, the problem becomes much more difficult. And the best known result is by Donna. So we have a similar setting, but we just change this AG2P to AG2Q. And the conclusion is that either U is contained in a line or U determines at least U over root Q directions. When this power S is even, when S is odd, we have a similar bound. So you can see that there is a huge gap between these two bounds, because the numerator is just about the size of the set, but the denominator here is a constant 2, whereas the denominator here is root Q. So there is a huge gap between these two theorems. And to prove this kind of theorems, we need to use a standard technique called a Rayleigh polynomial with Sonnen's extension. So this is also some kind of polynomial method, and they are first introduced by Rayleigh, and later Sonny extend Rayleigh's method and prove this kind of famous results. Okay, and next, let's consider the problem when the point set U is a Cartesian product. So in that case, we expect that the lower bound on the size of the direction set can be improved because U has more structure. So we can, the setting is that we consider two subsets of FQ, A and B. We call A, A1, A2 up to AM, and B is B1, B2 up to BN. Then the set of directions determined by this Cartesian product will be y2 minus y1 over x2 minus x1, where x1 and x2 are elements in A, and y1, y2 are elements in B. So because they are because the point set is a Cartesian product, you can see that the direction set is much easier to describe. And again, the direction set will be a subset of FQ union the infinity. And next, let's see the connection between the Cartesian product and the clique number of Paley graphs. Recently, the Benedetto, Soimoshi, and White proved that Cartesian product determine more directions. So recall that Sonnen's result is that if we have U points in AG2P, then the number of directions will be at least U plus C over 2. However, if U is a Cartesian product, then we can improve that bound to about the size of U. Okay, so that means the Cartesian product determine more directions. The lower bound have been improved to twice as the Sonnen's bound. Okay, and with this, we can try to see the connection between this direction problem and the clique number problem. The observation is that if C is a clique of generalized Paley graph PPD, then we can consider the direction set determined by C times C. The direction set is just C minus C over C minus C. And by our definition of generalized Paley graphs, each element of C minus C will be either 0 or this power in FP star. So because the division of because the quotient of two these powers in FP star is again this power in FP star, so the direction set is actually contained in this power of FP star union with 0 or infinity. So with this observation, we can see that the upper bound on the direction set is bounded by P minus 1 over D plus 2. And we can use this theorem to find a lower bound on the direction set, which is about the size of C squared. So we can set up inequality that roughly speaking is C, the size of C squared is bounded by P over D. So with that, we can recover Hansen and Petridis bound.
Okay. I'm a little bit confused about this C minus C over C minus C. Can you just maybe like say a little bit more about what's happening there and how it's not 0 over 0?
Oh, okay. So we know that each element in C minus C is either 0 or a this power in FP star, because that's the definition of the generalized Paley graphs.
Oh, I see. So this comes, so the fact that C minus C is non-zero comes from the definition of the Paley graphs, the generalized graphs.
Yeah. So yes, zero is an element in C minus V, of course. But if we pick two different elements in C, then their difference must be this power in Fp star.
I see. So the C minus C here, sorry, not to derail your talk, but the C minus C here means for every element in C, I take the difference of some element of C. I see. Okay, got it. Okay, thank you.
Yeah. Sorry for the confusion. Okay. Okay. So here the observation also works if we change P to Q because everything is identically the same. But the problem is that this theorem fails to hold when we change P to Q because of the following observation. So if E is a proper subfield of FQ and A minus A and B minus B are contained in this proper subfield E, then we know that all the directions determined by this Cartesian product will be in E union infinity because we can just treat it as they are embedded in the AG2 size of E. So that means if we consider this kind of particular Cartesian product, the direction set is bounded by size of E plus 1. So if A and B are at least about square root of the size of E, then this kind of lower bound on D fails to hold. So that means if we want to get something similar to this theorem, we must put some restriction on the set A and B. Okay, and that's what I did in the last few months. So I basically generalized this result to AG to Q, but we need to introduce more parameters. Okay, so the setting will be similar to the previous one. Let Q be a prime power and let A have size M, B has size N, where we assume 0 is including B for convenience. And we also suppose that K equals to Q minus Mn is a positive number. Unless we need to pick L, which is the smallest non-zero, which is the smallest non-negative integer, such as this polynomial f m k minus L evaluated at this set B is non-zero. So the definition of this polynomial fmt comes from Sony's extension polynomial. And the explicit formula for this polynomial fmt can be described by this equation. So it's very complicated and it's hard to study the distribution of roots. But we can just keep it as at this moment. And for this theorem, we need to further assume that one of the following conditions are satisfied. So the first condition is that any integer between m and m plus k minus l over n minus 1 is not a multiple of p. And the second condition is p does not divide m plus l. So if one of these two conditions are satisfied, then we can conclude that the number direction from determined by this Cartesian product is at least m times n minus n plus l plus 2. So the lower bound here is similar to the lower bound here. But as I have said, we need some restriction on the set A and B so that we can include something similar. So the additional assumption we needed is this condition or this condition. Okay, so the proof of this will be similar to this one. So I guess I don't have time to say the proof, but let's see how can we apply this theorem to our clique number problem. Okay, so again, we need one of these two conditions to be satisfied. And for condition 2, it may be difficult because we don't know the exact value of L. L is the smallest non-negative integer, such as this polynomial evaluated as set B is non-zero. But based on this explicit formula, it will be very difficult to study whether this is non-zero at the set B. So we can ignore this condition at this moment, and we can try to see whether the first condition can be satisfied at some cases. So basically, the first condition says that any integer between m and m plus k minus l over m minus 1 is not a multiple of p. So here we can get rid of l because we can bound it by k over m minus 1. So we don't need to worry about L. That's good. That's great. Okay. So, so the magic is that if m is equal to n, and if m is close to root q, then because k is q minus mn, then k will be very small. And again, we don't need to worry about L because k minus L can be bounded by k. Then because this number will be small, then that means this condition 1 can be checked. Okay, so we can apply this theorem in the case that m equals to n and m is close to root q to get this one. So again, we take this A and B to be the maximum clique of the generalized Paley graph. So we have m equals to n. And we know that the trivial upper bound will be root q. So we can safely assume that m is close to root q. So this condition can be satisfied. And to be more precise, I have this kind of theorem. So if we consider the clique number n of the generalized Paley graph PQD, then it must satisfy one of the following conditions. The first one is that n is amongst root q minus c. So that's great because the trivial upper bound is root q, and we are able to improve this by more than 1 because c here is between 0 and p minus over 2. And the second case comes from this condition. So if this condition fails to satisfy, then that means one of the this kind of consecutive integers is a multiple of p. So we want the first condition. We want the first condition to be true, which means we want the second condition to be false. And the idea is that if we pick C to be relatively small compared to P, then the number of integers here will be roughly 2C. But if C is much smaller compared to P, then 2C will also be much smaller compared to P. Now, if we pick a random integer, the probability that it is a multiple of P is about 1 over P. So that means if C is relatively small compared to P, then we can guarantee that we can imagine that the second condition won't hold in a positive proportion. And to be precise, we can define this capital P to be the set of primes, and we can define QRD to be the set of primes such as p to the r2r plus 1 is congruent to 1 modulo to d. So the definition of this QRD is just we want the parameter Q to be congruent to 1 modulo 2D. So that should be a natural definition. And we can use some tools from analytic number theory to show that this sequence is actually equally distributed modulo 1. So that means the fractional part of this p to the r minus half will behave randomly, and I guess it's uniformly at random in this interval 0 and 1. And finally, the theorem is that if we pick a positive function h such that hx is ox, little ox as x goes to infinity. So the purpose of doing that is that we want c to be much smaller compared to p, so that the number of integers here is has size little op. So we can try to use this kind of equidistribution result. And the final conclusion is that for any integers r and d, where d is at least 3, the clique number of this kind of generalized Paley graphs is bounded by p to the r minus half minus hp for almost all p in this set QRD. So recall that the trivial upper bound will be root q, which is p to the r plus half. But we are able to improve that by this kind of little op factor, which is non-trivial, because the previous best result is that it can be, the trivial upper bound can be improved by 1, but we are able to improve this by little op. So for example, we can pick this function hx to be x to the 0.99. Then we can show that for almost all primes, the clique number of this kind of generalized Paley graphs is at most root q minus p to the 0.99. So that's a non-trivial improvement on the previous trivial upper bound. Okay, so that's all I want to talk about today, and thank you very much for your attention.
Let's give Chi-Hoi a round of applause. Are there any questions about his talk?
You know the clique numbers of the Paley graphs of prime order. Like it starts out as 2, 3, 3, 4. Sometimes, however, it does go down. It's usually increasing, but it does sometimes decrease. Do you know why? If you just consider the primes here, you see 2, 3, 3, 4, but one of them it just, like for example, from 97 to 101, it's 6, then 5. Do you know why it decreases like that?
Yeah, I think the short answer is that the quadratic residue module a certain prime behave very differently for different primes. So you cannot say, for example, for let's see, for example, for for example, for this, where p is 229, the clique number is 9, and when p is 233, the clique number is 7. So roughly speaking, the clique number goes down because the distribution of the quadratic residue behave very differently for these two prime numbers. And you cannot say that if Q increase, if P increase, the clique number must increase, because that's closely related to the distribution of the quadratic residues. And we don't have a theorem says that the distribution of the quadratic residues for large primes behave very similarly to small ones.
Other questions for Chi-Hoi? Okay, great. If there aren't other questions, let's thank the speaker again. You can either unmute yourself and clap or just use the clap emoji. Thank you so much for that talk. I'm going to pause the recording.